Now that we know the basic terminology associated with sets, as well as the types of sets, let's talk about how these sets are related to each other and how they interact. For the purpose of this lesson, we use set A, which will have 1, 2, 3, and 4, and set B, which will have 4, 5, 6, and 7. Let's start with the intersection of sets. The intersection simply stands for the elements that are in both set A and set B, or whatever sets you're looking at. So, in this case, the intersection is written with this symbol, and it would be shown like this, where A has 1, 2, and 3, and B has 5, 6, and 7, but they both have 4, so the intersection part would be right here, where they both have the same element. Now, let's say that both A and B didn't have 4, so A would be just 1, 2, and 3, and B would be 5, 6, and 7. Then you would draw it like this, 1, 2, and 3, and B with 5, 6, and 7, with no connection in the middle because they have no elements that are in common. Now this means that the number of A intersect B is equal to 0 because there are no elements that intersect the two sets. Therefore, these two sets can be called mutually exclusive, which means that they have no elements in common. Another name for this would also be called disjoint. Now, let's talk about the union of two sets. The union is the elements which are in either set A or set B, or whatever sets you're looking at. It is written as A union B, and with our examples, it would look like this, where if this is A and this is B, then all the elements from 1 to 7, 1, 2, 3, 4, 5, 6, and 7 would all be included in A union B, because it's all the elements that are in either A or B. Now, all of this is great, but what if you're in a problem where the numbers you're evaluating are not in set A or in set B? However, you still need to keep track of it. So what would you do with it in a diagram? Well, that's where the universal set comes in, which is written as just U. Now, on a diagram, the universal set would be like a box outside of set A and set B, where if, say, you are evaluating all the numbers up till 10, 1, 2, 3, 4, 5, 6, and 7 would be in A and B, but 8, 9, and 10 would be outside but still in the universal set, because your universal set is all the numbers you're evaluating for the problem, which is 1 to 10. This brings us to the complement of a set, which is written as A naught if you're looking at the complement of A. On a diagram, this is shown by all the elements that are in the universal set that are not in set A if you're looking at the complement of set A. So specifically in our example, this would mean that since A has 1, 2, 3, and 4, all the elements that are not 1, 2, 3, and 4 in the universal set count as the complement of set A, which would be 5, 6, 7, 8, 9, and 10. Of course, some important considerations to be taken with the complement of a set is that A intersect A naught equals the null set, because by its very definition, the complement of A is all the elements not in A, so they can never have an element that is in common. On the other hand, the union of A and A naught is equal to the universal set, because it includes all the elements in A and not in A in the universal set, which is all the elements in the universal set.